case I wasn't clear. Okay, so the the first part of the PowerPoint, you'll have to just watch the videos. So starting from here, we're trying to talk about the difference between permutations and combinations because combinations are actually a part of um, what we're going to need in the middle of the binomial theorem. But also next class, we're going to have to do just some problems on permutations versus combinations. That's something that can occur on your HL test. Okay, just like strictly combination problems. So first of all, we're just gonna, it's been a long time since any of you guys had to think about probability, but permutations is the deal where order matters. And so the way I like to think about this, and it's gonna be kind of sad because I'm writing from the computer, but I like to think of prizes. Okay, because everybody's like, which one's which? Well, for prizes, you really care about the order. You care if you come in first, second, or third. Okay, whereas combinations, and when I get to that one, I'm going to tell you I think of committees, because if you're all on a committee, then you all have equal power. Okay, versus if you have offices, president, vice president, then it matters who gets what. Okay, so for permutations, when you're doing those, it's like prizes, you care about the order. So an example here is 8 horses are running a race, and it asks us in how many different ways can these horses come in first, second, and third, and assume there's no ties. You don't actually need a formula for permutations. You can just use what's called the fundamental counting principle. Somebody wake Megan up for me. And basically what you think about is there's 3 different positions that you can have. Now you've got 8 different horses. How many of them could come in first? How many choices? 8 choices. Okay, now one of them was first. So how many choices do you have left now? And so somebody was second. How many choices do you have left now? Okay, so you have a total of 336 different ways that those 8 horses could come in first, second, or third. So we're not talking about groups of how many different groups of 3 could win, but in fact, how many different ways they could get first, second, and third. So you could take the same 3 horses, rearrange them, and that's another permutation. There's a formula for this. The formula you need to write down. Okay, and it's at the bottom of the screen there. The permutations of n things take an r at a time, and you don't actually need the formula. Okay, you can just use logic, but it'll come out the same. So it's n factorial over n minus r factorial. I'm trying to painfully write this. Okay, and so for us, what we would be talking about is the permutations of 8 things taken 3 at a time. Okay, so we would have 8 factorial over 8 minus 3 factorial, which is just what? Okay, and you guys know from much more complicated math than this that you can rewrite this as 8 times 7 times 6 times 5 factorial. And then just cancel your 5 factorial. So the permutation formula is the same as the fundamental counting principle. Okay, you can just say, how many spots do I have? Just go down by 1. How many choices you have for each spot that you're talking about. Okay, so you do need the permutations formula. Any questions on that one? Okay. Oops. Okay, so now what it's asking is find the number of ways 5 people could be ranked first, second, or third in their class. So tell me what I would do. That's it. Okay, and so there are 60 different ways. How would I write that as a permutation? Can you do that on your calculator? Do you know how? Do we need to do it? They are right there by Cora. Okay, so you can just type it on your calculator, but you can also go through the menu. So if you go to Menu, Probability, Permutations, it comes up with NPR. You can just type that if you want to. But I'm going to put 5, 3. Oh dear. Well, there was a math competition yesterday, so you do Menu, Probability, Permutations. Okay, now you see that combinations is in the same spot, so I'm not going to come back to the screen again. When we get to combinations, I'm just going to expect you to do it. Okay. You can also get to factorial here, but it's kind of not necessary. Also, you can just type it if you want to. So you could do NPR, and it'll handle all the, you don't have to worry about like upper and lower case. But I like to go through the menu. I just think it's easy. And it just kind of fixes it for you. Okay. All right. So now I'm going to do a problem that has both permutations and combinations on it. So let's say that we have 4 people, Mary, Sue, George, and Tim. And we want to choose, we have a couple things we want to do. We want to choose a president, vice president, and treasurer. Sorry, it has a question mark after that. And we want to know how many possibilities there are. And we also want to know how many different ways we can make a 3-person committee. So yes, I actually typed out all the different ways you can make a 3-person committee. Okay. Actually, I didn't type out all the ways you can make a 3-person committee. What did I type out? Perfect. Thank you. Carl is saving me. I typed out all the ways they could have different offices. Okay, president, vice president, treasurer. In fact, if it was 3-person committees, I'd have a lot less choices. Okay, so let's just talk about, first of all, the different ways that we could have president, vice president, and treasurer. So how could I figure that out? Okay. And then what would that be as far as permutations or combinations? Okay. And so how many different ways should I have gotten? Did I? Okay. So those are the different ways that we could figure out, and I'll just go ahead and show the formula. This would be 4 factorial over 4 minus 3 factorial. Is that going to be the same thing? Yeah. Okay. And so you have that. So that gives you all the different ways that we could arrange these folks, these 4 people, to be president, vice president, and treasurer. But if I just wanted them on a committee, so I've got all these different ways, would any of these be repeats if they were just going to be on a committee? How many of them you think would be repeats? Pretty good guess. Okay, so what we want to do is take out the number of ways we've got the same people. They're just rearranged. So the number of ways that you can rearrange 3 people would just be 3 factorial. So basically, if you just take what you have and you divide by the number of ways that you can arrange people. So these are just the ways that you have the same 3 people just rearranged. So Sue, Tim, George just rearranged all the different ways would be 3 factorial. Okay, so then we're down to a lot less ways. What would that look like as far as permutations or combinations? Okay, so what they were kind of trying to show you on the video is that's the same as what you would get for permutations divided by the number of ways we can rearrange those 3 people the same number of ways. Okay, you could also look at it as just the fundamental counting principle divided by the number of ways you could rearrange those 3 people. You could also look at it as the formula for combinations, which you need to write down. Okay, which is just the same formula as you had before for permutations, only you're dividing by the number of ways you could rearrange those people, which is just r factorial. This is, there's a couple of symbols for it. So the most common one you see is the one I was doing here. You'll also notice it's written like this. It's written like this on your formula sheet. So if they write something like 5, 3, if we're not talking about vectors, which we will be talking about eventually, this does mean combination of 5 things taken 3 at a time. Okay, it's not like you're going to wonder, do they mean combinations or do they mean permutations? This is combinations. Okay, these are a couple of other notations. They're pretty easy to recognize just because they have the C's. It's just this one everybody doesn't necessarily recognize just because it doesn't have the C for combination in it. Okay, so that's just the basic difference between combinations and permutations. Combinations is what we're going to need for binomial theorem. But like I said, next class, they actually have, these are really simple problems. I assure you they have some mind-spinning ones for combinations and permutations that we're going to have to do next class. Okay, but there's no or. We're going to do, but today we're just going to look at how combinations tie into the binomial theorem. Okay, so if we think about just having 2 terms, if you raise it to the 0 power, it's 1. Somebody's going to have to help Megan. If you raise it to the 1st power, it's just yourself. It's just what you get the same thing you started with, right? If you raise it to the 1. You know how to expand a binomial. So here they're just showing me the expansion for each one of these. Okay, and you guys should already know the pattern because you learned it a couple of years ago. Do you know what would happen in the next row, or can you tell me some patterns that you either see or remember? Okay, so you said, Cora said 1, 5, what? Okay, how'd you get that? Okay, so you have a 1 on each side, and then you added the coefficients that were above it to get the middle ones, and you knew that from pre-calculus. But what was there something that you learned about? Pascal's triangle. Okay, so you guys already know that. What about these powers? Like if you were predicting for the next one, x plus a to the 5th, and sorry this looks so gross, but it's the best I can write from my computer. What would my first one be? Okay, and then what? Cute little a. Okay. Oh, this looks so bad. And then and then and finally. Okay, so what we notice is that we're going to start this, the first term in the binomial starts with the highest power and it goes down by 1 every time. And then the second term in the binomial starts out not at all or to the 0, and then it raises a power every time. Okay, and so you guys have learned that. And we're going to see if we can take this a little further. Y'all are already geniuses on all this. Okay, so you guys already knew about how the pattern works for Pascal's triangle, how you start with the 1, 1, 1, and then you always have a 1 on the outside. And actually, I think if I click, this might show that, maybe not. But how if you add these, you'll get this one. Add these 2, you get the 3. Add these, you get the 3, and so on. The connection that might not have been made as much is the fact that these are the same as combinations. So this guy right here is the combination of 0 things taken 0 at a time. These are the coefficients that I need if I'm raising something to a 0. All I would need is the fact that that's going to be 1 no matter what. Okay, on this row, this is the combination of 1 thing taken 0 at a time, one thing taken 1 at a time. So this is also the coefficients that I need for a plus b to the 1, because it's just going to be a plus b. Okay, this guy, 2 things taken 0 at a time, 2 things taken 1, 2 things taken 2. So what's nice about this is if I know that I'm raising something to, say, just give me a number. If I'm raising it to the 100, I know that on Pascal's triangle, all I need to know is it's going to be 100 things taken 0 at a time, 100 things taken 1 at a time, 100 things taken 2 at a time, all the way up until I get to 100 things taken 100 at a time. Okay, so that's really convenient. Like, if you're just raising to a pretty low power, 3 or 4, something like that, it's easier to write out Pascal's triangle to get your coefficients. But if you're going to like the 100th row and they just want the 14th term, it's going to be a lot easier to know the pattern that when you're raising to the 100, this is the same as combinations. 100 things taken 0 at a time, 1, and so on. Okay. Okay, but I'm going to do one in a second where we try to find one particular term like I'm talking about, but we're going to do this first just for expanding. Okay, so if we're doing to the 3rd power, remember that the first row gives you to the 0th. This gives you to the 1st. This gives you to the 2nd. And this would give you what you need to the 3rd. So when you guys expand this, and I'm going to let somebody kind of fill it in for me up here in a minute, you know you're going to need 1, 3, 3, 1. But can you also tell me what this would be for combinations? Perfect. Okay, so anytime you don't want to write them out at Pascal's triangle, if it's too high up, that's one thing you can do. And then what are you going to do with the 2x? Okay, what's it going to be raised to? Okay, you start out with the first one raised to the highest and go down by 1 every time. You either don't write it here or you say 2x to the 0. And then the other one, second one, you're going to have to treat that as negative 3y. So you'll have negative 3y. So it's to the 0 at first, so you don't write it. To the first. To the second. Should have used a different color. Kind of sad. I feel like I'm the equivalent of Jack and Tam Jude writing on the quote board when I try to write with pen on this. Just a little shout out for you there. All right, so then that's all you have to do. You've written it out. You are going to have to, simplify stuff like that. And I promised somebody could come up, and I didn't do it, but that's all right. We'll get you on something. So this would be 8x to the 3rd. So help me out on these. We're going to have 4, 3, 12 times 3, negative 36. You're supposed to say yes or no. Thank you. All right, what about the next one? Thank you. This looks like a kindergartner is teaching you guys. What's the last one? Thank you. Okay, so that's pretty easy to expand. Let's see if that's my last one. Okay, you guys do this one real quick. See how it goes.
Hello everybody, it's Cora. Michael's actually doing the problem, but we can't reach, so I'm doing it for him. And so first he's writing the combination, I'm pretty sure. He's taking a different approach than I did, but that's okay. We're just going to roll with it. You don't actually have to write the 2. The 2 to the 0 is just 1. I think everybody knows that 2 to the 0 is 1, Michael. Well, that would be an issue. Michael's yelling at me, if you were wondering. He just told me I was a filthy liar. So he's just expanding. I don't really know what to narrate. Well, the pattern in the combination would be that he just started at 4 over 0, and then he goes up by 1 each time. He goes up a degree. And then the next one, I feel like I'm yelling. And then the next one, for the x part, it starts at x to the 4 and goes down by 1 power every degree. Then a, which is 2 in this case, starts at 0, which Michael very wrote out for us so we can see that. Oh, you didn't write out 2x squared to the 0. Everybody's going to be confused. And then that goes up by 1 every time. So now he just has to simplify. Thank you. I was confused. I didn't know that 2x squared went to the 0 went to 1. He's giving me really mean looks right now. The combinations in this happen to be the same thing that you get in Pascal's triangle. That's how this works. Yeah, you can. He's showing that 4 over 0 is 1 in Pascal's triangle, and that's what he's notating currently. You're simplifying really big. Michael is writing very unevenly. The simplification. Oh, he realizes that he did the wrong thing. Oh, he erased everything. Oh, okay. That was awkward. As you can see in our decreasing font, that is our answer to this expansion.
All right, good job, team. Okay, so when you look at the binomial theorem on your formula sheet, this is what it looks like. I apologize, it looks a little grainy. I cut and pasted it and then tried to make it larger. I should have just typed it over. But these are n's, so this is the expansion for a plus b to the n. And so if you look, they've got a to the n, and what's happening to the power of a? Yeah, it's going down by 1 every time, and then it's not here. So technically it's a to the 0. So they're trying to give you the pattern that it's starting with a to the n, whatever the first term is, the power is going to start, raised to the highest power, go down by 1 every time until it's to the 0 or not there. They're also showing you with the b's, it's starting out to the 0, which they don't show because that's just 1. And then it's b to the 1, b to the 2, b3, all the way up to get to whatever it's raised to. Okay. Also, as far as the combinations, they don't show you n things taken 0 at a time because that's just 1. But it's going to have the pattern we talked about. N things taken 1 at a time, taken 2, taken 3, taken 4, all the way to n taken n at a time, which is just 1, which is right here. Now, it's really handy that they give you just a general form in the middle. For a lot of the problems that they're going to ask you to solve, they're going to say, find the coefficient of x to the third and the expansion of some crazy thing raised to the 15th. Okay, and you're not going to know actually which term that occurs in, and this part of the formula is going to help you figure that out. Okay, that's the main kind we're going to do, but not the first kind we're going to do. Okay, so an example is, forget all that. They want you to find the fifth term of x plus a to the 12th. And it's honestly pretty rare. The IB questions will usually say, find the coefficient of, say, x to the something. But this particular problem is asking me for the fifth term. So this is what I use for a general formula. So I'm just going to write that. N things taken r at a time. And basically on this, you know almost everything. And the tricky part is always to figure out what r is. Okay? So for me, I can identify easily that this is N, this is A, and this is B. Okay, because this is A. In my formula, the first term is referred to as A, the second term is referred to as B, and the power is referred to as N. Okay, so the deal is I have to figure out what R is for the fifth term. So R, if you notice its position, is whatever's down here. Okay, so if you notice, this is for the first term, what is R? Perfect. R is 0. Thank you, Michael. Second term, R is what? Okay, so what do you think R is going to be on the fifth term? Nope, 4. Okay, notice that R is 1 down from whatever your term number is. Okay, so for us, R is just 4. So I appreciate that. Okay, so for us, instead of, even though we know how to write out the expansion of this, and it's really trivial, we don't want to write out the expansion if we don't have to. We can go straight to the term. So it would be a combination of 12 things taken 4 at a time. My A is x, okay, to the n minus r, so that's 12 minus 4. And my second term, which is A, to the 4. Okay, and we could use our formula to figure out the combination of 12 things taken 4 at a time, or y'all could be nice and figure it out on the calculator for me. It's what? Perfect. Okay, so just from the calculator, combination of 12 things taken 4 at a time. And so that's a lot less trouble than writing it out, even though we know how to. Okay, so you definitely could write it out. You could write out the Pascal's triangle all the way to the 12th row, which you have to start with 0, but all the way to the 12th row. But that would be a pain. What? There's a what? Oh, 2 X's. I'm sorry. Thank you. My bad. That's an A. The people are shouting that I am wrong. Okay, but this is definitely a lot easier just to go to that one spot. Okay. Yes, I have. I was trying to remember if I had. Okay. Okay, this is just them telling you the same thing we did. Okay, this is, by the way, if you're wondering, if you were going to expand it all out, you certainly could, but certainly that's a lot easier. Okay, now what I want to do, I have a worksheet, but I want us to do the first couple together because they're actually harder than anything I just showed you. I am. Okay, have patience. We are here. Just anywhere on my desk is fine. All right, folks, don't give up on me. We've got it coming. I don't know why this is taking so long. Pause it. Okay, so this is your homework sheet, and it has the binomial theorem at the top, and we are going to use that to find some of the various different things that they ask us for. Okay, so it's really, really handy. If you take a look, this first one's going to be pretty easy because we already did one like it. It wants the 10th term. And again, this is from your formula sheet. This in particular is a general term. I'm sorry, Michael, what? Yes. I'm gonna pick a couple of random ones and then let y'all finish. Okay, so for this one, we can identify they just want the 10th term, so I definitely don't want to expand this all the way out. If I did expand it all the way out, how many terms would there be? How many? Too many and 18. Okay, so it's always one more term than whatever your power is raised to. So we're going to look at this. This guy right here is going to be your A. This is your B. This is your what? N. So the key is we got to figure out what R is. Okay, if it's not too hard, 10th term, R is going to be what? 9. Okay, but remember, Michael, you can look at the formula up here. So if you look, yeah, this is the first term, and that's N0. Okay, so the R is in the position right here. So the second term has an R of 1. It's just always one less because we started with 0. So once you know that, this guy is really easy. And I'm just going to take this general term. This is my favorite part of this formula. Okay, so I'm going to do n things taken r at a time. So 17 things taken 9 at a time. I'm going to take my a, which is x, raise it to the n minus r. Okay, so 17 minus 9. And then if there's a negative there, you've got to include it. So it's going to be negative 2 over x raised to the what? Perfect. Okay. Who wants to help out with 17 things taken 9 at a time? Okay. And then we would have, I guess, x to the 8th. What about negative 2 to the 9th? Okay. And I was just raising the numerator and the denominator. So if you put that all together, you do want to combine your x's. So when you divide, you subtract your exponents. So that would be x to the what? Perfect. And these two numbers multiplied together? Okay, well, it helps when you can put commas. Okay, so negative 12,446,720 x to the negative 1. Okay, and if you'd rather write the whole constant over x, that would be the same thing. Okay, so that's it's kind of easy because it tells you 10th term. What's a little bit harder is this kind where it says find the coefficient of x to the third in this expansion. So the problem is you don't know where x to the third is going to be because each term has a combination of the x squareds and the 1 over x like multiplied together, and you're like trying to figure out which one of the terms will end up multiplied together to give you to the third. Now I have to tell you, r can only be 0 through 6. You've only got a limited number of choices, but we're going to be very matter-of-fact about it and go straight to the right one. I will tell you guess and check is a thing that can be useful. I don't want to ignore it because sometimes it's faster. But I'm going to take just the general term part of this and write that down. And I'm just going to write down everything that I know because I'm going to want one particular term of this. But n is definitely going to be what? 6. I don't know what r is. A is definitely what? Perfect. To the 6 minus r. B? Okay. And that's to the r. So really, if I just could figure out what r is, this would be perfect. What I have to do is figure out r so that this comes out to be, the combination of these two things comes out to be x to the third. So basically, you're figuring it out. So x squared is raised to something, and the x in the bottom is raised to something, so that they cancel out correctly to come out to x to the third. And you can do this with the formula. okay, that you got right in front of you. Basically, what I like to do is ignore any part of this that's a constant because I'm only trying to figure out like what would r have to be to make the x's come out right. You can sit here and guess a couple of r's. It doesn't take that long to do that. But this part is going to be a constant. The 2 is going to be a constant. So I like to take the x squared to the 6 minus r. I don't care about the negative 3. And I just take the x, the 1 over x part. And I'm trying to figure out if I just deal with the x's, what would r have to be to come out to x to the 3rd. So I'm just kind of like reducing it down to that. And so this is pretty easy to solve. When you raise to a power, what are you doing with your exponents? Multiplying. So this would be x to the 12 minus 2r. And then this I like to write as x to the negative 1. So then when I raise it to the r, what would it be? And then when you multiply, what are you doing with your exponents? Adding them. Okay, so you'd have x to the 12 minus 2r plus a negative r. So what's that all together? Okay. What do you think I'm going to do now? Perfect. Okay, so just set the exponents equal to each other and solve that. So what is r going to be? So once you know what r is, okay, all you got to do is go back to here and put it in. Now I'm not going to worry about, because I don't have to work this other problem, but you might want to do it at the bottom so you don't run into the space of this problem. But you're just going to do 6 things taken 3 at a time. 2x squared to the 6 minus 3, so 3. Negative 3 over x to the 3. If you figure that out, you've got the right term. Okay, so anybody want to help out with 6 things taken 3 at a time? Okay, and then 2 cubed would be 8. X squared cubed would be x to the 6. Negative 3 to the 3rd would be negative 27 over x to the 3rd. If you notice, we did this correctly, because when you divide, you subtract your exponents, that's x to the 3rd. If we didn't get x to the 3rd, we know we messed up. So we just need 20 times 8 times negative 27. Okay, and they just asked for the coefficient of x to the 3rd. So there it is. Now, I have had people, if they ask a question like this, sit there and expand the whole thing out till they found it, and they get it right sometimes. Sometimes they mess up. But you guys, that's mostly in SL. In HL, you have so many more problems to work on this HL exam that you better use the efficient way to get to the part. They don't, honestly, usually ask you to do like to the 100th. It's usually something fairly low. And again, if it's faster for you to sit here and just try a couple of R's to see which one would make your X's come out to x to the 3rd, that's okay. Okay, this is, you have lots of serious things to work on, so whichever's more efficient for you. Okay, so we're going to turn over to the back. I'm just going to do 2 more, then I'm going to leave you all alone and let you finish it. Okay, so this one asks for the constant term. So if it's the constant term, essentially x is raised to the what? 0. So you just do the same thing, only x to the 0. Do you even want me to do it, or do you want to try it first, or do you want to do it together? Okay. Okay. All right, so basically I'm going to take that same part, and I don't have to memorize this. It's on the formula sheet. I just love, love, love that they give me just kind of the standard pattern for the middle term. It's just kind of handy. Okay, again, I like to fill in everything I know. So I know that this is A, this is B, and this is N. Okay, so this would be 6 things taken R at a time. A would be 2x squared to the n minus r, so 6 minus r. B is your second term. Make sure to include the negative. And that's to the r. And I want that to come out to be something x to the 0. So I'm just going to look at the parts of this that have the x's in them, ignore anything that's a constant. So I don't need this, I don't need the 2. I need the x squared to the 6 minus r. I don't need negative 1. Since we've already done this once, I'm going to go ahead and write this as x to the negative 1 to the r. And I just want to figure out what r is for this to come out to be x to the 0. Okay, so raised to a power, multiply my exponents, it'd be 12 minus 2r, x to the negative r equals x to the 0. Add my exponents, so I'd have x to the 12 minus 3r equals x to the 0. And then, just like before, set my exponents equal. R would be what? Okay, and then just go and substitute in your r into what we already did. Okay, so 6 things taken 4 at a time. 2x squared to the 6 minus 4, so 2. Negative 1 over x to the 4. 6 things taken 4 at a time. And then times 4, x to the 4th, times negative 1 to the 4th would just be 1, so 1 over x to the 4th. We should not be surprised that those x to the 4ths cancel. Okay, so, oh yeah, sorry. So you get 60. So that is your constant term. And then we're just going to do one more, the one right after it, and then I'll let you work on the rest of them. The negative 1 was to the 4th, so that made it positive. Okay, so the last one says expand and simplify, so I definitely do need to write out all the terms. And it says to give my answer in the form a plus b squared roots of 3, where a and b are elements of the integers. Okay, the z stands for integers. So basically, if it's to the 5th, how many terms can I expect to have? 6 terms. So I'm going to leave myself 6 spots. I always space this out poorly. Cora, this will be a challenge for us. Fitting things in. I always wish I had more room in one of them. I'm definitely going to have 6 spots. I could go on Pascal's triangle right now, but I'm not going to because I know the coefficients are going to follow a pattern with combinations. What's the pattern going to start with? Perfect. 5 things taken 0 at a time. So we got that just from whatever it's raised to. So then just continue the pattern. 5 things taken 1 at a time. 5 things taken 2. 5 things taken 3. 5 things taken 4. 5 things taken 5. Okay, you know the first and the last are going to come out to be 1. The other ones you can put in on your calculator. You could also have found the correct row on Pascal's triangle. That's allowed too. Okay, you're going to start with the square root of 3, and it's going to be raised to the what? And then we start going down a power every time. And the last one is square root of 3 to the 0, but that's just 1, so I'm not going to write that one. Okay. Then I'm going to start with 2, and it would be raised to the 0, which is just 1, which I'm not going to write. And then 2 to the 1, 2 to the 2nd, 2 to the 3rd, 2 to the 4th, and 2 to the 5th. So the pattern's pretty easy. We just have to simplify it to be in the form that they want. I think it'd be best to kind of go through and figure out these coefficients. I know this is 1 and 1. Again, it's not too far down on Pascal's triangle if you want to do it, but this is the row whether it's 1, 5, 10, 10, 5, 1. Okay, or you can do it on your calculator, combinations, 5 things taken 1 at a time, 2, 3, 4. Okay. Now, square root of 3 to the 5th is what we need to figure out. So what's the square root of 3 times the square root of 3? 3. So I'd have 2 sets of those. 9 root 3 is perfect. So I would have 1 times 9 root 3. Okay, and then square root of 3 to the 4th. So this guy would just be 90. Okay, square root of 3 to the 3rd. Yep. Okay, so that would be 120 root 3. Square root of 3 squared. Okay, you don't have to be afraid to tell me because it's too easy. 3 and 8, so 240. This one just has the square root of 3. 2 to the 4th is 16. So 80 square roots of 3. And finally, this guy's 32. Okay, so they just want me to combine like terms. And when you do, you get 362. When you add all your square roots of 3's, you get 209 square roots of 3. And it just said give your answer in this form, so you don't have to say A is 362 and B is 209 because we gave it in that form. So there you go.